In this video, I just want to really quickly touch base on some of the weird things that we actually saw in those last couple of examples. Namely, we're going to be looking at this idea of where is a function differentiable and where is it not differentiable. The first thing we actually have is one of these kind of classic theorem statements, which is going to say if a function is differentiable at a point A, then it must be continuous at that point. What that theorem's actually telling me is that this idea of differentiability is a little bit cooler than being continuous. And earlier when we talked about continuous functions, we said that these functions are really nice. These are these classic functions that you can draw without picking up your pencil. They're very nice functions that occur all over the place. In this case, we have this idea that a differentiable function is even a little bit nicer. They're somehow better than continuous functions. These are the ones that are not only continuous, but they're doing these things very smooth. I don't have any crazy jumps or kind of really sharp corners or anything bad actually occurring. In this case, these differentiable functions are very, very nice. A way that we're actually going to say this theorem a lot is actually going to be using what's referred to as the contrapositive. And if you're not familiar with some of this kind of logic terminology, the idea is that if you have one of these if-then statements, which is referred to as a conditional statement, what I can do is I can create what's referred to as the contrapositive. And the way you take this is you're going to take this if-then statement, flip it around, and negate everything. In this case, the contrapositive of that last theorem is going to say if a function is not continuous at A, then f is not going to be differentiable at A. What this gives us is a really easy way to break this idea of differentiability. Namely, if you have a giant jump occurring, one of these jump discontinuities, well, I have that function's not going to be continuous there, which immediately tells me that I'm not going to be differentiable there. That is kind of the really easy way to break this idea of differentiability, is to break the idea of continuity. However, there are a few other ways that we can break this idea of differentiability without breaking continuity. And we saw two of those actually back in the kind of creation of some of these derivatives. Namely, we can have these really sharp corners or kinks or cusp or whatever you want to call them, these points that my function is changing direction very quickly. At those points, we actually do not have a tangent line, and therefore we're not going to be differentiable there. If you think about this kind of absolute value of x graph, this giant V, you can very nicely draw this thing. It's a nice continuous function. I just drew that thing without picking up my pencil. But this thing is actually not going to be differentiable. The reason is that if you try to draw some tangent lines down there, you have too many of them. You have really no idea what to do at that cusp. And that's going to give us this bad point. It's kind of these kinks or these corners, these things that are changing direction way too quickly. In that case, I'm breaking this idea of being differentiable. The other thing that can actually occur is this idea of having a vertical tangent line. Kind of on that same bandwagon of if I'm trying to draw in one of these kind of tangent lines, if I get to this point where I have a vertical tangent line, well, that thing has an undefined slope, and I'm going to break down this kind of case of being differentiable. And the example that we saw, the kind of painstaking example that we went through, was this giant cubic root of x function. And we saw that that thing actually has one of these vertical tangent lines occurring right at 0. In that case, I have a very nice continuous function. It's this giant s, but it actually does have a point where it's not differentiable. So they're not always equal. This idea of continuity and differentiability are not the exact same thing. This differentiable is actually a fancy or a cooler term in this case, whereas continuous is very, very nice, but it's not nearly as nice as differentiable. Kind of if you think about making a hierarchy of functions, differentiable is a very nice thing. It's sitting near the top of this kind of cool tree. Visually, we do actually just have these kind of three things that kind of all come together, the kind of ways that we can break differentiability. The first is going to be that easy one, this idea that you're just a discontinuous function. If you're discontinuous, you're immediately not going to be differentiable there. The other two cases are the weird ones where you are actually continuous, but you're not going to be differentiable. In this case, you have this corner or this cusp. You have too many tangent lines at that point, and it's going to be a bad point in that case. And the last one's going to be this idea that if you have one of these vertical tangent lines, that is, you have this point where your slope is going to be kind of undefined. You have this perfectly vertical tangent line that's also going to break this kind of idea of differentiability. It's not breaking the idea of continuity. It's still a perfectly nice, smooth curve in that case, but it does have this kind of vertical tangent line.